Now we'll discuss find the gain of simple current mirror. Finding the gain of simple current mirror is nothing but simply you are finding about the current gain. So the ratio of output current to input current, or the ratio of output current to reference current of a simple current mirror. And we know the principle of simple current mirror, where we are going to use two transistors, both are exactly identical, and when the aspect ratio, that is W by L ratio, is same, at that time we expect similar currents in both transistors. That is nothing but mirror of input current results in output side. So two identical mass devices with equal gate source voltages and operating in saturation will carry equal currents if we neglect channel length modulation, that is lambda is equal to 0. This is a simple current mirror we have discussed. M1 and M2 are going to be identical transistors with W by L ratio equal. I reference is the input current, I out is nothing but output current. Since we are applying same VGS for M1 and M2, this is M1 and it is for M2, so I out is nothing but I reference. If we neglect channel length modulation, we can write the reference current equation and output current equation like this. I reference is nothing but I, the current flowing through this M1 transistor, which is in saturation. So we know the equation for saturation region. I is equal to beta by 2 into VGS minus VT whole square. Beta is nothing but transconductance. The transconductance is going to be considered as K into W by L. K is nothing but mu into COX. So here 1 by 2 mu n into COX of W by L of first transistor M1 into VGS minus VT whole square. VGS is nothing but for both same, so we are not writing VGS1 or VGS2 like that. VGS minus VT whole square. Both are identical transistors, so that threshold voltage is also equal. Similarly, you can write for I out. I out is same 1 by 2 mu n COX W by L of second transistor into VGS minus VT whole square. Now, if you get the ratio of I out to I reference, what you are getting is W by L of 2 by W by L of 1 into I reference. This is general current equation, current gain equation of simple current mirror. I out is going to be exact replica of I reference, or it may be multiples of I reference. If W by L of 2 is W by L of 1, at that time I out is exactly equal to I reference. Otherwise, if W by L of 2 is going to be greater or smaller than W by L of 1, so that I out you may be getting lesser than or more than reference current. So we can get the output current as equal to reference current, or less than reference current, or greater than reference current. So this equation is valid only when channel length modulation is neglected. If you consider channel length modulation, how to write the equations? If channel length modulation parameter, that is lambda, which is not equal to 0, that is now considering the effect of channel length modulation. Channel length modulation is nothing but for the given gate to source voltage, as VDS increases in saturation, ID also increases. If we neglect ID is constant in saturation region for the given VGS minus VT, even VDS increases. So if we consider channel length modulation effect, we have to consider VDS effect on ID. So these are the resulting equations for ID1 and ID2. ID1 is nothing but I reference, ID2 is nothing but I out. So 1 by 2 mu n COX into W by L1 into VGS minus VT whole square into 1 plus lambda VDS1, and for I out it is 1 plus lambda VDS2. This term we are adding extra 1 plus lambda VDS1 for ID1, 1 plus lambda VDS2 for ID2. These terms are going to be effect of channel length modulation, so that if you get the current ratio of simple current mirror, at that time it is not only W by L of 2 by W by L of 1, and this is now multiplied with 1 plus lambda VDS2 by 1 plus lambda VDS1, where we are assuming lambda is going to be identical for both transistors. If lambda is not identical, lambda 1 and lambda 2, if we are taking separately at that time, the equation you can write it as id2 by id1 is w by l of 2 by w by l of 1 into 1 plus lambda 2 VDS2 divided by 1 plus lambda 1 VDS1. So this is the current equation, current gain equation of simple current mirror without channel length modulation effect and with channel length modulation effect. This is how to calculate gain of simple current mirror. Now we'll go for the second important point, that is nothing but output resistance. Find the output impedance of simple current mirror. The figure shown is simple current mirror. For that one we need output impedance. Output impedance is nothing but simply it is the ratio of output voltage divided by output current. So to calculate output impedance, the general way is you have to apply a test voltage at output terminals so that no other voltages are going to be influencing this one. That's why any input voltages or input currents must be treated 0. That is, voltage sources are going to be shorted and current sources are going to be open circuit at input side. So we are considering only output terminals. For that one we have to apply some test voltage. That test voltage makes some current to flow in this circuit. That is, we are assuming it as test current. If we get the ratio of test voltage to test current, at that time the resulting is nothing but output impedance. So how we are going in this way? We are assuming that one Vx is nothing but test voltage, Ix is nothing but test current. So the ratio of these two things is nothing but R out. R out is equal to Vx by Ix, where Vx is test voltage, Ix is the current flows into output terminals as a result of Vx. So to calculate R out, first step you have to replace this simple current mirror with small signal equivalent, and then you have to apply test voltage. Then you can calculate the output impedance. So first aim is to draw the small signal model of simple current mirror. Simple current mirror will be consisting of Q1 and Q2 transistors. We will go with step by step. First we will draw small signal equivalent of Q1. Later we are going to replace that small signal equivalent. Then we will draw the small signal equivalent of Q2 like that. Then we will apply the test voltage calculating the output impedance. So first step, small signal equivalent of Q1. Small signal equivalent of Q1 is nothing but this is the portion what we are going to be replacing. A reference current I in that is flowing into Q1. Q1 is nothing but diode connected transistor whose gate and drain are going to be shorted. So for this one we have to write the equivalent model and we have to replace this one with equivalent circuit. This is small signal model for Q1. I in is nothing but a current source, that is a constant current, so that is modeled as open circuit. So I in is not present in the small signal model. I in is a constant current which can be modeled under AC terms, AC analysis. Open circuit, any constant current will be treated as open circuit, so that I in doesn't appear in the small signal model. And Q1 is nothing but this is VGS. Small signal model of Q1 is nothing but generally any MOSFET it will be consisting of input terminals gets open circuit because of silicon dioxide layer which is present between gate and channel that doesn't allow any current from gate to flow into channel side, so that always gate current is 0. Gate current is 0 is nothing but input current is 0. Input current is 0 is nothing but input impedance is infinite. Input impedance is infinite means input side is open circuit, so that only voltage exists but no currents are going to be existing at input side. So input side is nothing but gate source side. So this is VGS1. Input side is open circuit since no gate current flows. And output side there will be a current source. That current source is nothing but ID1, that is equal to transconductance times of input voltage. So ID is equal to GM1 times of VGS1 followed by a resistor of RDS1. And since this is small signal model, now we will minimize this one by applying. We are going to calculate the equivalent resistance of Q1 by applying a test voltage and resulting test current. So Q1 is diode connected transistor, that is whose gate and drain are going to be shorted. That means it is always in saturation. Under saturation, if you neglect channel length modulation, under saturation, if you neglect channel length modulation, output current is constant irrespective of output voltage. Output current is constant is nothing but output impedance is infinite. The small signal output impedance is infinite when channel length modulation is neglected. So RDS1 is nothing but output impedance of Q1 transistor, that is going to be treated as infinite, that is open circuit. So there is no current is flowing into this side. The total IY which is coming from VY is flowing into this GM1 VGS1 only. It doesn't go into RDS1 since it is diode connected transistor, and which is going to be giving ID constant. ID constant in saturation means RD output impedance is infinite. So the current is only flowing through GM1 VGS1. By that time, if you get the ratio of VY by IY, simply IY is equal to GM1 VGS1, and VGS1 is nothing but voltage from this point to ground. Voltage from that point is nothing but what you are going to be applying is VY. So VGS1 is nothing but VY. IY is equal to GM1 VGS1. So that IY is equal to GM1 VY we can write. So IY is equal to GM1 into VY. So the ratio VY by IY is nothing but 1 by GM1. This is what we'll get. So entire Q1 configuration can be replaced with only a resistor of 1 by GM1. So this is very important result. Whenever a diode connected transistor is there, that is whose gate and drain are shorted, by that time it is always modeled as a simple resistor with resistance value of 1 by GM1, where GM1 is transconductance of Q1 transistor. So reciprocal of transconductance is nothing but impedance of diode connected transistor. This result we are going to use throughout this subject. Now we have to draw the small signal model for the entire simple current mirror. This is a simple current mirror. Till now what we have seen is nothing but a part of simple current mirror, that is Q1 side. So now Q1 side is can be replaced with 1 by GM1. So this Q1 side we are dividing it into two parts, Q1 side and Q2 side separately. Q1 side is nothing but it is simply replacing with 1 by GM1. Q2 side, Q2 side is nothing but it is again it is small signal model of MOS FET. Input side is open circuit, output side there is a current source followed by a parallel resistance. Since it is Q2, so we are writing it as VGS2, GM2 VGS2 as current source, RDS2 as output impedance. Now to calculate impedance of this current mirror, output impedance of current mirror, we must apply some test voltage, that is what Vx, and which results in Ix current. The ratio of Vx by Ix is nothing but output impedance. Look at this small signal model carefully. What is the value of VGS2 here? What is the value of VGS2? The value of VGS2 in this small signal model is 0, because look at this one. VGS2 is nothing but voltage from this point to this point, that is nothing but it is in parallel with this resistor. So voltage across this resistor is nothing but voltage drop across these two terminals. So VGS2 is nothing but voltage drop across 1 by GM1. Since it is open circuit, no current flows through this 1 by GM1. As there is no current is flowing through this 1 by GM1, VGS2 is nothing but 0 into 1 by GM1, that is VGS2 will become 0. So voltage drop across this one is 0 as there is no current flows, so that VGS2 is 0. Whenever VGS2 is 0, this current source GM2 into VGS2 will also become 0. That is nothing but it acts as open circuit. So this circuit is 0, this circuit is 0. What we left is nothing but only RDS2. Are understanding this point? So simply VGS2 is 0 as there is no current flowing into 1 by GM1. And since VGS2 is 0, this current source is neglected because it is resulting in 0. GM2 into VGS2 is 0. 0 current source is nothing but open circuit. So this is open circuit, this is neglected, and here the only the component results is RDS2. So entire simple current mirror can be treated as a resistor equivalent, and the resistor is value is output impedance of Q2. So output impedance of Q2 is nothing but output impedance of simple current mirror. Remember that one. Output impedance of Q2 is nothing but output impedance of current mirror. So this is the final conclusion. Entire simple current mirror can be replaced anywhere with a single resistor whose value is nothing but the output impedance of Q2 transistor. Now if you calculate output impedance of current mirror, you have to apply Vx and Ix. From that one you are calculating RDS2 like that. So R output impedance of current mirror, simple current mirror, is nothing but RDS2. This is the final conclusion. Any current mirror can be replaced with a single resistor. Otherwise, any single resistor can be replaced with current mirror. Are understanding this point? Any passive resistor can be modeled with current mirror, or any current mirror can be equivalently modeled with a passive resistor whose value is nothing but output resistance of Q2. By varying V out and I out, we can get this RDS2 value, desired one. So conclusions from this simple current mirror are: small signal output impedance of simple current mirror is always RDS2, which is nothing but output impedance of M2 transistor, Q2 transistor. And current mirror can act as a current source with very high output impedance as desired. Current mirror is acting as a current source. Generally, ideal current source is going to be having infinite impedance across its terminals. So ideal current source, it is going to be having its input resistance as infinite. So here current mirror is going to be acting as current source. By that time, if it has to be ideal, it should have infinite impedance. That is nothing but for this one, it should have high output impedance practically. So RDS2 is going to be very high practically. Since variation in output current is very small, even though a large variation of output voltage is taking place. For a large variation of output voltage, practically a small variation in output current takes place in saturation region. That's why RDS2 is very high, ideally it is infinite. Current mirror can also act as active load. In place of passive resistor, you can use current mirror. By that time, that resistor is modeled as current mirror, so that current mirror is going to be active element. That's why it is treated as active load. So Till now we have discussed about the two important parameters of simple current mirror. First one is calculation of gain. Second one is calculation of output impedance. And third important parameter of current mirror is V naught minimum. What is meant by this V naught minimum? V naught is nothing but output voltage. Output voltage is nothing but output voltage is voltage across M2 transistor and that too across output terminals. So this is M2 transistor and these two terminals, drain and source of M2, are going to be treated as output terminals. Voltage across drain to source is nothing but V out or V naught. Output voltage is nothing but voltage across drain to source of M2 transistor. For proper operation of current mirror, M1 and M2 must be in saturation. M1 is definitely in saturation because whose gate and drain are going to be shorted. So there is no chance of getting any other region for M1. Always it will be in saturation. So there is no problem with M1. Whereas M2, the whose gate and drain are going to be not shorted. By that time we must ensure that one M2 should operate in saturation region. How to say what is the condition for M2 to be in saturation? So from this current mirror, first important point what we can see is VDS1, drain to source voltage. VDS1 is equal to VGS1, that is equal to VGS2. Both are having same gate to source voltage, but we cannot say that one VDS2 is equal to VGS2 because the circuitry fed across M2 transistor. But for stable output current, that is for proper operation of current mirror, we must get I out stable. I out stable is nothing but it must be in saturation region. Both transistors must be in saturation region for stable output current because only in saturation region currents are constant. M1 is always in saturation as its drain and gate are shorted. To keep M2 in saturation, the condition is drain voltage should be greater than gate voltage minus VT. VDS2 should be greater than or equal to VGS2 minus VT. You must apply the voltage across drain to source as either equal to VGS2 minus VT or greater than that one. If it is greater, definitely M2 will be in saturation. If it is equal also, M2 will be in saturation. So the minimum voltage what you can apply across M2 such that M2 will be in saturation so that it is acting as current mirror is nothing but V naught minimum is VGS2 minus VT. This is V naught minimum. Ideal value of V naught minimum is 0, but for this simple current mirror we are getting V naught minimum as VGS2 minus VT. So V naught minimum should be as low as possible to get higher gains, higher voltage swings. Advantage of active load current mirror over resistive load. Already we have seen applications of current mirror in the last class where we are going to show where we have seen common source amplifier, how it is replaced. The load of common source amplifier is replaced with current mirror. Common drain amplifier, how the load of common drain amplifier is replaced with current mirror, and like that differential amplifier and some other thing wherever a passive resistor is there that can be easily replaced with current mirror, so that current mirror whenever it is replaced it is treated as active load. The advantages of active load over passive load, that is resistive load. First one, to achieve similar gain with resistive load much larger power supply is required. To get more gain at that time normally we require more power supply if you are going with passive resistors, but there is no need for current mirrors because the resistance value can be increased to get the higher gains. That resistance value is usually large for current mirror since it is in saturation. Second one, large resistor requires large chip area while fabrication. So if you want to get large passive resistor. At that time it occupies a larger area while fabrication, and it can be realized with only two transistors. Active load current mirror can be realized only with simply two transistors. The disadvantage of active load current mirror: output impedance, we are assuming that one it is high, but it is not large enough. Even though it is high, ideally it should be infinite, but it is not that much large. So we have to improve this output impedance so that it can act as ideal current source. These are the advantages and disadvantages of current mirror over passive resistors. Now we will see how to implement current mirror using PMOS FET. If you implement current mirror with n-MOS FET, that is treated as current sink, where the drain current is sinking into ground. When we use current mirror with PMOS FET, it is called as current source, that will source the current for the rest of the circuit. How to connect PMOS FETs and how to implement current mirror using PMOS, that we will see now. This is a circuit diagram of PMOS current mirror. For PMOS transistor, the important point is source is always at higher potential than drain. Always current flows from source to drain. Remember these 2 points. For PMOS FET, always source is at more high voltage than drain, and always current flows from source to drain, because always current flows from higher potential to lower potential. So this is always current flows in PMOS FET from source to drain. So this is PMOS FET. This bubble signifies that one it is PMOS transistor, where we are using two transistors, one is M1, the other is M2. Now source is at higher potential, this is ground and it is VDD. So VDD is going to be connected to source. So above is nothing but source, below is drain. Above is source, below is drain, and this is drain and it is gate. So drain and gate are shorted for M1. So M1 is always in saturation. M1 is always in saturation in case of PMOS current source also, because whose gate and drain are shorted. And gate to source voltage here, we don't call it as VGS, we call it as VSG, because source is at higher potential. VSG is nothing but this is VSG, voltage across source to gate. VSG, VSG, VSG. And for this M2 transistor, this is gate and it is source. So this is VSG2, this is VSG1. So we are applying same voltage for M1 and M2. So same source to gate voltage, so that if we assume M1 and M2 are identical transistors and whose gate to source voltages are exactly same, so that they will be giving the same currents. The current flowing through M1 is also flows through M2, whose whenever M1 and M2 are identical transistors with equal W by L ratio, so that this I naught current can be given to any other circuit, so that it can source that circuit. So always reference currents are generated with this help of this diagram. So a PMOS current mirror is used to generate the reference currents. Now PMOS current source is going to be acting as a current source with value as I naught, that is flowing in M2 transistor. It is comes from VDD. So this is equivalent diagram, equivalent model of simple current mirror. It is schematic, this is equivalent one. And the output current equation of PMOS can be written like this. PMOS equations for the MOSFET to operate in saturation region. It is same as NMOS equations, where we are writing it as, instead of VGS, we are writing it as VSG minus VTP, like this, VSG minus VTP. And this is the equation when channel length modulation is considered. If it is neglected, lambda will be 0, so that the term will not appear. ID will be equal to KPP by 2 into W by L into VSG minus VTP whole square. If channel length modulation is neglected, if channel length modulation is considered, this is the equation shown. So this is regarding calculation of three important parameters of simple current mirror. One is current gain, the other is output impedance, and the last one is V naught minimum required to keep the output transistor in saturation such that stable I naught results. And after that one, what we have discussed is how to implement PMOS current mirror.